So I did that already for you on this page. I didn't want to make us sit here and write it all out, but let's just kind of walk through it. Okay, so we say now here, theta is a function of x and y. So we're going to make the assumption, because we satisfied all the conditions, that we have homogeneous boundary conditions in one direction. The problem is linear. The domain is simple, right? All those assumptions that we had to make, if we satisfy those conditions, we can then make the assumption that we can separate this into a function of x and a function of y separately, and then solve for them independently, right? We went over that last time. So, okay, we say we've got this function of x and this function of y. And then we're going to substitute this assumption into our equation here. And we end up with, right, the partial with respect to x on one term, the partial with respect to y on the other term. And then we say the partial derivative with respect to x means that y can come out here. The partial derivative with respect to y means that x can come out here. And we divide everything by theta x times theta y. Okay, and then that gives us the thing down in the left-hand corner. And then we end up with what's in the right upper right here, which is we've now separated this equation into a function of x and a function of y. Right? We follow that? Exactly the same thing we did last time. Nothing has changed except for now we're calling this theta instead of t. Okay. All right, and then we say that these both, in order for this equation to be true, these things both have to be equal to a constant. Remember why that was? It's because if I change something here, the only way that I could change something here and this still remains true is if both of them are equal to a constant. So then we call that constant lambda, or lambda squared, in order to indicate that it's definitely a positive number, that lambda. And then we have d theta x is either minus or plus lambda squared theta x. D theta y squared is either plus or minus lambda squared y squared. And then we have to make sure to pick the sign according to whether it's a homogeneous direction or not. Right. And remember, now you've been through this process, so you can probably see why we did this now. We have to pick the sign on the homogeneous direction such that we get the periodic function that lets us get the eigenvalues to solve in that direction. And then the other side, just the non-homogeneous side, kind of comes along for the ride. Okay. So to get the periodic function, which is sines and cosines for this type of problem, we pick the positive in the homogeneous direction, which was x. Right? Again, we could have homogenized in y had we had the right conditions there, but we did it for x. So this becomes our eigenproblem here. Right? This is the ODE that we're trying to solve in the x direction to get our eigenvalues. Okay, we went through that kind of quickly, but hopefully that everybody's following. Okay. All right, so then step 3, let's pick back up here and actually solve this eigenproblem. In the x direction, we have d squared theta x dx squared plus lambda squared theta x to get our c1 sine plus c1 or c2 cosine. If that's the solution to that particular ODE. So now our task is to go through and start enforcing the boundary conditions to solve the eigenproblem. So let's restate what we have here. So we have theta at x equals 0 is equal to 0. That was one boundary condition. The other boundary condition was minus k partial of theta with respect to x at x equals w is equal to h bar theta at x equals w. Those were our two boundary conditions that we're dealing with. Right, what was the step here that we had to do? We're saying theta is a function of x and y. We're only concerning ourselves now with the x part of this problem. So we actually need to sub back in our assumption that theta x times theta y is the true form of theta, and restate these boundary conditions as needed. So we'll say theta x at x equals 0 times theta y has to be 0, right? That's just restating that boundary condition based on our assumption that we have theta x times theta y. theta y is not changing as a function of position x, right? Theta y is a single function only in terms of y. So when we're looking at just the x part of the boundary condition, that can divide out. It's effectively a constant that we can divide out. So we end up with theta x at x equals 0 is equal to 0. Okay, so that's our, seems trivial, but it's our restatement of this boundary condition in terms of our assumption theta x times theta y is the form that we're going for. Okay, so that was the first boundary condition over here. This is 1. For 2, we have to restate this on that same assumption. It's kind of an equally simple thing to do, but we say minus k. So we have now theta x times theta y. Theta y is a constant, so it becomes theta y times the partial of theta x with respect to x at x equals w is equal to h bar times theta x times theta y. So theta x is at x equals w. So now on both sides of this equation, we have theta y, which again is not changing as a function of position x. So this can cancel out of this equation. Okay, and then our restated boundary condition is just minus k d. Right now, the normal differential operator, no longer partial, d theta x dx at x equals w is equal to h bar times theta x at x equals w. Right, so those are our two x direction boundary conditions that we've now restated in terms of theta. Questions on that? Okay, I mean it's like a lot of words to basically just tack an x on in the subscript. Okay, but for the problems we're doing, that's basically all we have to do here. I think there's other situations where that's not the case, so we just kind of are pedantic about it. Okay, so now let's make myself some room over here. So let's go through and actually solve to try to get the Eigen condition here. We're going to enforce the boundary conditions first. We're going to say theta x at x equals 0 equals 0. So let's enforce this boundary condition on our temperature solution or our theta solution, right? So theta x at x equals 0 is equal to C1 sine of lambda times 0, it's x equals 0, plus C2 times cosine of lambda times 0. Right, and that all has to equal 0. 0 is equal to that. All right, so let's see. This evaluates to 1. This evaluates to 0. So we're saying here C2 is equal to 0. Okay. So then we're left with our expression theta x is equal to C1 times sine of x. That's what we can move forward with here. Okay, second boundary condition. We're going to say minus k times d theta x dx evaluated at x equals w is equal to h bar theta x at x equals w. So now let's so evaluate the derivative, right? So the derivative now of theta x is what's the derivative of sine of x? Well, it's just, oops, sorry, I missed a lambda up there, didn't I? So sorry, theta x is sine lambda times x. Sorry about that. So what's the derivative of that function? It's just cosine, lambda times cosine. Okay, so we end up with, here we have minus k times lambda times C1 times cosine of lambda w, right? We're evaluating this at w, is equal to h bar times C1 times, what is my theta function? It's just sine lambda w. Okay, so now we have eliminated the x from this equation, and we're left with something where we can solve directly for C1. Okay, we solve this out, and we end up with the Eigen condition. So actually C1 goes away, and we end up with minus k times lambda over h bar. I should bring the h bar over. is equal to sine over cosine less tan of lambda times W. Okay, so this thing here, right, this is, we enforce the boundary conditions to be able to figure out what the lambda values are going to be, our eigenvalues. So this is our eigencondition. Eigencondition is the equation that you need to satisfy infinitely many times to get your lambda values out of it. So this is our eigencondition. Questions on this? Yeah. You mean over here, this part over here? I think you need to think through and convince yourself that for the boundary condition that you have, that what you're evaluating doesn't depend on y. Okay, I mean, so this is just a useful step to confirm that mathematically, right? But you want to make sure that, yeah, y is changing as a function of position y, but y is not changing as a function of position x. Therefore, the things I'm doing here are valid for the position where x equals 0 or x equals w, kind of regardless of what y is doing. But that's fundamentally the premise, is that it's valid no matter what you're doing for y. So I guess the short answer to your question is probably you can just, write it out that way, or skip that sort of verbose way of writing it. We'll do it here just to prove the point. Okay, I don't think I would take away points for that on grading it. Okay, so we have our eigencondition. If you remember last time or the previous times we've solved these problems, what we've had is an eigencondition where you can kind of look at that problem and you can see that for certain values, it would say like, pi over 2 or 3 pi over 2 or whatever, that you can kind of by inspection see where that problem is true or where that statement is true. Here now we have a situation where we have k times lambda over h, that's something where lambda is on the left-hand side, but then we also have lambda in the argument for tan. So we can't explicitly solve for lambda and get a bunch of different eigenvalues. So you have to take a slightly different approach for this in order to figure out what those lambda values are. But it doesn't end up being super complicated or anything. It's just we need to make sure we find all the lambdas that satisfy that equality statement. And it's not trivial to do by inspection. Okay, so that's our next step here. So let's look at, here's our eigencondition here. That's what we just decided we had. So how do we actually solve this if we can't explicitly solve for lambda? Well, it turns out we can use a tool like ease, or you could do any other root finding software. But the underlying idea is that let's take here what's on the right-hand side, okay, and let's take what's on the left-hand side. Notice here I've actually multiplied by w over w so that we can do this in terms of the product lambda w. Okay, just kind of to normalize it a little bit. So let's take what's on the left-hand side, plot that, and let's take what's on the right-hand side and plot that. Where those two lines or those two plots intersect each other, that's where this equality is true, right? So here I've got, trace it out. So here I've got tan lambda w, right? Here we've got lambda w, got tan lambda w. It's a periodic function. So that's the right-hand side. And then I also plot on the same plot what's on the left-hand side, right? This is what's on the left-hand side. It's a linear equation. So where do these things intersect? Well, they intersect here at 0. They intersect here. They intersect here. That position lambda w is the eigenvalue where those intersect. That's the lambda is where that equality is true. Okay. So we can use ease if we can provide a reasonable guess value. If we provided a reasonable guess value for lambda times w, we'd start off, ease would start off somewhere around here, and it'd be kind of searching to find the equality, and it would probably find, you know, that point if we provided a reasonable guess value. But the problem is you'd have to do that infinitely many times. So your solve e's, write down your lambda value, solve it again, right? And you'd pretty quickly hate me if you don't already. So that would not be the ideal way to do it, but ease has a better way of dealing with this. And actually any root finding thing, you can just put in a program that updates your guess value every single time and solves for that root. Okay, let's look at how to do this. So the first thing we need to do before we go to ease, let's look at you know, what are the kind of the constraints on this problem. So I'll draw this with green. So let's pick this line here. This, if we continued plotting tan, we would see that there's this period where it's possible for this intersection to happen. Right? There's a period from pi over 2 to, what is that, 3 pi over 2? Right? In that region, we know there has to be a solution. And then shift again from 3 pi over 2 to 5 pi over 2. There has to be a solution in that region. Right? The tangent is periodic on that scale. So we know if we're providing guess values, we have to say, okay, from pi over 2 to, you know, lambda 1 is going to be from pi over 2 to, I guess, what, pi? No, it should be pi over 2. Yeah, this should be 3 pi over 2. And then from 3 pi over 2, lambda 2 has to be 5 pi over 2, and so on, right? So we have this rolling window where we know the solution has to live. Okay, so let's take this. Oh, sorry, one last thing before I do that. So let's write out the rolling window. It's going to be 2I minus 1 times pi over 2. It has to be lambda I times W, and then that has to be less than I times, oops. Yeah, I think, sorry, this I think is wrong. It should be 2I plus 1 minus 1 over 2. I'll have to come back. I'm not going to fix it now, but I think this limit might be wrong. We'll come back to that. But anyways, the idea is that you can compute the bounds and then put that into ease and solve it. So let's look at ease now and see how you'd actually do this.